What specific problem does your hybrid approach combining PINNs and cylindrical approximation aim to solve in the context of functional differential equations, FDEs, and how does it address the limitations of existing numerical methods?
Our hybrid approach combining physics-informed neural networks, PINNs, and cylindrical approximation aims to address the significant computational complexity and limited approximation ability associated with solving functional differential equations, FDEs. Existing numerical methods, such as functional power series expansion and discretization-based techniques, often oversimplify solutions or impose severe restrictions on the class of input functions and functional derivatives, leading to inadequate expressivity and convergence issues. In contrast, our method transforms FDEs into high-dimensional partial differential equations, PDEs, using cylindrical approximation, which we prove to converge reliably. By leveraging PINNs, we achieve a substantial reduction in computational complexity from OM-6 to OM-R, where R is typically 1 or 2, thus allowing for a much broader range of input functions and functional derivatives to be accurately represented. This innovative combination not only enhances the expressivity of the approximations, but also ensures that the solutions and their functional derivatives are accurately captured, as demonstrated in our experiments with the functional transport equation and the Burgers-Hoff equation.
How does the proposed method or algorithm work? Please illustrate the steps in detail, focusing on both the cylindrical approximation and the application of PINNs to solve the resulting high-dimensional PDE.
The proposed method consists of two main stages: the cylindrical approximation and the application of physics-informed neural networks, PINNs, to solve the resulting high-dimensional partial differential equations, PDEs. In the first stage, the input function is expanded using an orthonormal basis, transforming the functional differential equation, FDE, into a high-dimensional PDE of the expansion coefficients. This process is known as the cylindrical approximation, where the functional is approximated by truncating the series expansion at a finite degree, allowing for the representation of functional derivatives as well. The convergence of this approximation is rigorously proven, ensuring that as the degree of approximation increases, the solution converges to the original FDE. In the second stage, the derived high-dimensional PDE is solved using PINNs, which are capable of efficiently approximating solutions in a mesh-free manner. The inputs to the PIN include time and the coefficients from the cylindrical approximation, while the output is the approximation of the solution. The PIN is trained by minimizing a loss function that combines the residual loss from the PDE and the boundary loss from the initial conditions, utilizing automatic differentiation to compute the necessary derivatives. This two-step approach significantly reduces computational complexity and extends the expressivity of the approximation, allowing for the handling of a broader class of input functions and functional derivatives compared to traditional methods.
Can you provide a simple yet illustrative example that walks through the inner workings of your proposed algorithm, particularly demonstrating how a specific functional differential equation is transformed and solved?
To illustrate the workings of our proposed algorithm, we can consider the functional transport equation, FTE, as a specific example. Initially, we represent the input function, theta x, in terms of an orthonormal basis, such as Legendre polynomials, leading to the expansion, theta x equals sum underscore k equals 0 caret m1 a underscore k phi underscore kx. This transformation allows us to reformulate the FTE into a high-dimensional partial differential equation, PDE, involving the coefficients, a underscore k, which we denote as f bold symbol a, t. The cylindrical approximation is then applied, yielding the approximated equation, f bold symbol a, t equals f underscore 0 p underscore m theta, with the initial condition, f bold symbol a, 0 equals f underscore 0 bold symbol a. Finally, we solve this high-dimensional PDE using physics-informed neural networks, PINNs, which efficiently approximate the solution, f bold symbol a, t, and its functional derivatives, achieving a typical relative error order of sim 10⁻⁻3. This process demonstrates how our hybrid approach effectively reduces computational complexity while extending the expressivity of the solution space.
What are the main theoretical and practical advantages of your approach over existing methods, particularly in terms of computational efficiency and the scope of input functions that can be accurately represented?
The main theoretical advantage of our approach lies in the convergence proofs we provide for both the approximated functional derivatives and the solutions of functional differential equations, FDS, under the cylindrical approximation, ensuring its reliability for FDE applications. Practically, our method significantly reduces computational complexity, requiring only OM*R, compared to the state-of-the-art carbon monophosphide ALS algorithm, which demands OM*6. This reduction allows for a substantial extension in the class of input functions and functional derivatives that can be accurately represented, increasing the degrees of polynomials or Fourier series used for approximation from 6 to 1000. Additionally, our hybrid approach utilizing physics-informed neural networks, PINNs, enables efficient mesh-free solutions to high-dimensional PDEs, further enhancing computational efficiency. Overall, our model not only improves accuracy but also broadens the applicability of numerical methods for FDEs across various research fields.
How did you validate or test the effectiveness of your proposed approach, including the experimental design, datasets used, and metrics for evaluating performance on the functional transport equation and Burgers-Hoff equation?
To validate the effectiveness of our proposed approach, we conducted numerical experiments on two functional differential equations, FDEs, the functional transport equation, FTE, and the Burgers-Hoff equation, BHE. We utilized analytic solutions for both FDEs, which allowed us to compute absolute and relative errors, essential metrics in numerical analysis. The experimental design involved a 4-layer physics-informed neural network, PIN, with specific activation functions and a total loss function combining smooth L*1 loss. We employed Latin hypercube sampling for training, validation, and test sets, and set parameters such as =0, ρ_0, overline mu, and sigma squared to specific constants for consistency. Our results demonstrated that the model achieved typical relative error orders of sim 10⁻⁻3 for both FTE and BHE, indicating a significant improvement in accuracy and the model's capability to represent input functions and their derivatives effectively.
What specific results did you achieve using your method on the functional transport equation and the Burgers-Hoff equation, and how do these results compare to state-of-the-art methods? Additionally, what limitations did you encounter with your approach that may affect its applicability in broader scenarios?
Using our proposed method, we achieved typical relative error orders of approximately 10⁻⁻3 for both the functional transport equation, FTE, and the Burgers-Hoff equation, BHE, even with polynomial degrees as high as 1000. This performance significantly surpasses state-of-the-art methods, such as the carbon monophosphide ALS algorithm, which can only handle polynomial degrees up to 6. Our approach demonstrated the ability to accurately approximate not only the solutions, but also their functional derivatives, showcasing a notable improvement in expressivity and accuracy. However, a limitation of our method is its reliance on the choice of basis functions, which can influence computational efficiency and may restrict its applicability to specific types of FDEs or boundary conditions. Additionally, while our model performs well within the tested scenarios, the generalizability to more complex or less structured FDEs remains to be fully explored.